Okay, this is Mr. Waterman, Lafayette High School, regular physics, and today I'm going to talk about the last two equations of motion that we've been working on. We've got three equations of motion so far, and where do they come from? Well, we did the slope of a displacement time. That gave us velocity. Then we did the slope of velocity time. That gave us acceleration. That's where we got this little guy right here. And then we left off and we actually did an integral, or we found the area of a velocity time, and we got this equation number 3. And that is the true sort of mathematical definition, is the area of a velocity time function is displacement. And this is basically the area of a simple trapezoid. But that's all well and good. What about these last two equations? Well, the last two equations is just kind of smoke and mirror algebra is all it is. But they turn out to be some very useful equations. Now, all I'm doing here is I am just making an algebraic substitution of equation 2 into 3. So this expression for V initial is going to get substituted in right there. And, if you want to, write this in your notes, good. If you want to follow along, that's just as good also. Okay, so there's my substitution. There's this term for V final put in there. Okay, so let me combine like terms and smoke and mirrors of algebra and chant some incantations and blah, 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 blah. If you want to do the algebra, you just go have yourself a good old time, and distribute the T and everything. But whatnot, I come up with this guy right here. And this is a really sort of go-to equation to find distance whenever I have a uniform acceleration. Okay? Now, the only thing you have to be careful of is you may have to divide your time interval into chunks that have uniform acceleration. We've kind of done that before with velocity, right? If I have velocity change, I had to break it up into chunks where I had either a constant or a smoothly changing velocity. Got to do the same thing with this equation too. Right? That's how we avoid calculus in this course. All right, so this is a very good equation. It's one of my go-to equations. But there's one I like even better. And this one really is a heavy hitter. Okay, so what I'm going to do now is I'm going to start with the equation 2 again. And with equation 2, I'm going to substitute that into equation 3 again, except I'm going to do a little bit something different. I'm going to solve this for time, just an algebraic rearrangement for time. And I'm going to substitute it into time here on equation 3. Okay, so I'm going to tag that thing on there. Okay, there's equation 2, solve for time. Okay, there's my substitution. Algebra, smoke and mirrors, chant incantations, cloud-like terms. Hey, I even had to FOIL on this one. And then I simplify it, and I get this guy. Now, what is so cool about this one is it does not involve time. Whenever you're solving motion problems, time is a key piece of data. You'll notice out of 4 of our magic 5 equations, we use time. Okay, so that kind of wraps up your magic 5 right here. What I consider you should do is you should take the magic 5 and you should make a 3x5 card and keep it very handy with you at all times when you're solving motion problems. I mean, throughout the course. All right, let me show you mine. Here's my 3x5 card. And this comes in very, very useful. Okay, if I have this in front of my face and I'm solving motion problems, then I can narrow it down to what I need really quick. You might want to make some notes, like for instance, this is only good when velocity is constant. These are only good if acceleration is constant. You have to maybe break it up into time intervals if your acceleration is not constant. Look for hints. Starts at rest, v initial equals 0. Comes to a stop, v final is equal to 0. Okay, before we finish this video off, I want to say one last thing about acceleration, particularly the direction of acceleration. Okay, notice how I've got arrows over all these guys, got lazy here. But these are all vector quantities. Now, the easiest vector quantity is the relationship between displacement and velocity. Velocity and displacement must share the same direction. Acceleration, not true. So how do I figure out which way acceleration is going? And we're going to go over this in more depth, but it is extremely important, and we have to get it down. All right, direction of velocity is just simply look at the direction of your displacement vector. Displacement vector, a vector divided by a scalar, does not change the direction of the vector. It only changes its magnitude. Direction of acceleration, okay, well, we're going to go over this vector dance later, but the vector dance is all about finding the direction of acceleration. And the key is to look at the direction of velocity. Next, what is velocity doing? And for the purpose of this, I only wanted to do two things. It can get bigger, it can get smaller. Okay, so let's see what I mean here. Okay, key is always to look at velocity. Let's say I have a velocity vector going that way, and the velocity vector is getting bigger. Okay, you go, oh, well, yeah, it's accelerating. Well, yeah, good for you. It's accelerating because it's changing velocity. So if the velocity is going this direction and it's getting bigger, that means that the acceleration vector is going the same direction. So if we say these guys are going in the positive direction, then in our equation, we're going to assign the acceleration positive. It's going to the right. Okay, now, let's say I'm going fast and my velocity is decreasing. Okay, it's getting slower and slower and slower. Maybe it's even coming to a stop. Okay, and you go, oh, that's deceleration. Never use deceleration in this course. Okay, what I want you to do is I want you to say the acceleration is in a negative direction, right? Never use the word decelerating. I'm going to show you why. Let's say velocity is going the other way, and it's getting bigger. Okay, so these guys are all going in the negative direction. Okay, so what happens is my acceleration is in the same direction because the velocity is getting bigger. Let's say my velocity is in the negative direction, but it's getting smaller. Okay, so all these guys are pointed in the negative direction, but getting smaller, and that means acceleration has to go in the positive direction. Okay, so basically, if velocity is getting bigger, this scenario, acceleration is pointed in the same direction. Whenever velocity is getting smaller, the acceleration is pointed in the opposite direction of velocity. Huge, huge, huge. So when you're using your Magic 5, that's going to help you determine a positive or negative sign that goes in for your accelerations. Okay, hope this helps. This should get you good to go for your UT Quest assignment.